Hello everyone, welcome to the lecture 40 in the course Diffusion in Solids. So, this is the last lecture of this week 8 and therefore, it is going to be a tutorial lecture. We will talk about some problems based on the concepts that we studied. So, the question number 1 is an advantage that SIMS technique offers over the radiotracer diffusion. The first is measurement of low diffusivity. So, this if you then the second is measurement of isotope effect, high sensitivity, post diffusion annealing characterization. So, here the correct answer is D, because the low diffusivity you can also measure using radiotracer technique if you use sputter sectioning specifically. The isotope effects also can be if the isotopes are available, then radiotracer technique can be used. And the sensitivity of radiotracer is in fact higher because you are counting the radioactive nuclei. So, but the post diffusion annealing characterization, because once the sample is contaminated with the radioisotopes, you can not usually put it in a normal SEM or a TEM or XRD. So, usually that is not possible. Moving on to the question number 2. Which of the following factors can cause deviation from Gaussian profile during a radiotracer experiment? So, this we talked about that when you have the thin film condition, usually the expression that you obtain for the diffusion is C equal to C naught exponential minus x square by 4 dt. That is the standard expression. But if you have certain factors involved, then you have a deviation in this Gaussian profile. So, let us see what are these, which of the options are correct. So, remember in the tutorials I am not mentioning specifically which problems have or which objectives have multiple or a single choice answer. You have to basically understand. Please read the question first without looking at the answer and then try to attempt it. So, the evaporation of matrix atoms, it does cause a deviation in the Gaussian profile according to this relation. So, this particular term takes into account the deviation or the evaporation of the matrix atom. Similarly, evaporation of tracer atoms also cause the deviation in the Gaussian profile. This is the Gaussian profile equation. The remaining is the evaporation of the tracer, where K is a constant related to the evaporation constant. Then contribution of dislocation diffusion. Remember in the video we did not talk really about the dislocation diffusion, but we have seen or we will rather see when we talk about the dislocation diffusion in the coming lectures, that also is a path available for the diffusion of atoms, and hence if the dislocation diffusion is present in significant amount, it can cause a deviation in the Gaussian profile. So, although in the actual video it was not mentioned specifically, but please remember that dislocation diffusion can also cause a deviation in the Gaussian profile. It is usually an expression like this is followed. And then the grain boundary diffusion also can lead to additional slope in the diffusion profile, which is given by which varies as x to the power 6 by 5. So, basically all these 4 factors can cause the deviation in the Gaussian profile. So, A, B, C and D all are the correct answers. The question number 3, which of the following statements are correct? This is about the spectral and resolution and data acquisition rate in WDS and EDS. So, in the video we talked about this comparative advantages and disadvantages. So, you can see that WDS has a high spectral resolution, the energy which is 2 to 6 electron volt. That is why you see that there is some of the cases the elements can be distinguished very nicely. The other side of it is that the acquisition rates, the data acquisition rates are much slower in EDS than in WDS than in the EDS. So, WDS, because of the geometry of the detection, and it uses the wavelength. So, you have a slower rate of data acquisition. So, the correct option in this is A and D. Question number 4. Which of the following techniques are suitable to measure diffusion coefficient of the order of 10 power minus 20 meter square per second? So, we have seen this graph in the very first lecture of this week. So, which gives you the range of diffusivities various techniques can measure. So, here so remember that when I asked 10 power minus 20, it is not that I am asking you to memorize that number, but you should understand that when you talk about solids, 10 power minus 20 is usually comes in the lower range of the diffusivities, and therefore, the techniques which are suitable for measuring the lower diffusion coefficients are you should know which are the techniques which I can use to measure the diffusion coefficients which are of the low values. So, techniques are like secondary ion mass spectrometry and the radiotracer diffusion using sputter sectioning. The electron probe microanalysis and the mass spire spectroscopy you will see are more suitable for the diffusion coefficients of the higher values. So, the correct answer here is A and. Question number 5. The reduction of diameter before mechanical sectioning is done to negate the effect of. So, this reduction of diameter is talked in terms of the context of radiotracer diffusion, and in the radiotracer diffusion, after the annealing is done, usually we saw that the reduction of the sample diameter is done using a setup like this, where this is your grinding paper, the sample rotates on this, which leads to the reduction in the diameter. This is done to negate any of the lateral diffusion effect. So, that means when you drop the tracer during your diffusion annealing through the surface, some of the tracer can reach the circumference. Then when you are measuring the section thin layer or the average concentration in each layer, then this can give a additional or a erroneous contribution. So, to ensure that you are measuring only the one dimensional profile and neglect any lateral diffusion, we go ahead with the reduction of the diameter of the sample. So, the correct answer is C. Question number 6. TOF SIMS is based on the fact, so TOF is time of flight. TOF SIMS is based on the fact that ions with the same energy but different masses travel with different velocities. Hence, the time taken by an element to reach the detector after getting sputtered off is proportional to. So, the time of flight detector in SIMS is based on the fact that isotopes of different masses, if they sputter off from your sample, if the energy is same, then they will reach the detector with a different velocity because the mass is different. So, the heavier the atom, the mass, it will take more time to reach the detector. But that way you will see that both option A and C should be possible, which is the exact relation. So, that exact relation is determined by this conservation of energy equation, which gives that T is equal to D into root m by 2 q v. So, therefore, it is proportional to square root of mass. So, the correct option is the answer A here. Moving ahead, in the context of WDS detector, the difference between the Johann and Johansen geometry is the relative position of source and detector, relative position of source and analyzing crystal. Analyzing crystal is bent and grounded in Johansen geometry, while it is only bent in Johann geometry, or the relative movement of the source and the detector. So, in this if you see the schematics of both the Johann and Johansen geometry, you will see that Johann geometry the crystal is bent to the radius 2r, but in the Johansen geometry it is not only bent, but it is also ground to the radius r. So, the bending it is bent to the radius 2r, but it is ground to radius r as well. So, the option whereas the remaining options, if you see, the specimen and the source, everything else is same in both the geometries. So, therefore, A, B and D are not correct, the only correct option is C here. Moving ahead to question number 8. So, which of the following statements are true regarding the mean relaxation time during the energy dissipation in an inelastic solid? So, tau is basically, if you see, the mean relaxation time tau is written as root of tau sigma into tau epsilon. Now, tau sigma is the stress relaxation time and strain relaxation time. So, this is the geometric mean. So, the option A is not correct. It is not an arithmetic mean. It is a geometric mean of the stress relaxation time and the strain relaxation time. Now, the second is it increases exponentially with increasing temperature, or it decreases exponentially with increasing temperature. So, the relaxation time tau is thermally activated, and tau is proportional to exponential delta H by kBt. Now, here be very careful when you are analyzing this expression, because remember that we are used to more the Arrhenius type of relation, where there is a minus sitting here. But when we talk about the time, then in the time there is no minus here. The relaxation time, there is no minus. So, usually when the moment I have seen students making this mistake, moment you see the exponential something by kBt, you immediately say that it is exponentially increasing with temperature. But that is true if minus is there. So, now if minus is not there, then you see that as you increase the temperature, then you decrease this overall fraction. And if you decrease this overall fraction, there is an exponential. So, the overall this term decreases. So, the exponential of delta H by kBt will decrease as you increase the temperature. So, therefore, the correct option is that it decreases exponentially with increasing temperature. So, please be careful in seeing this expression. Do not just blindly take. See carefully whether the minus is there or not. So, the correct option in this case is B and D. The next question is which of the following statements correctly represents Haven ratio? The symbols have usual meaning. Di is the intrinsic diffusion coefficient, dGb is the grain boundary diffusion coefficient, the sigma d sigma is the charge diffusivity, d star is the tracer diffusion coefficient. So, we have when we were talking about the electrical methods, we saw that the Haven ratio is basically the ratio of the tracer diffusivity to the charge diffusivity. So, the correct option is D. Moving to question number 10. Which of the following materials are usually amenable to diffusivity measurements using spreading resistance profiling? So, when we were discussing this method, we saw that this is usually employed, or this is employed for the semiconductors. Okay, semiconductors which have the foreign atoms which are electrically active, those are the type of materials which are amenable to the diffusion measurements using SRP. Now, among the options given, the semiconducting materials are silicon and gallium arsenide, and therefore, the correct option is B and C. Consider the Bloch equation shown below, which terms represent the rate of relaxation of the magnetization. So, the Bloch equation is given here, which is dm by dt equal to gamma m cross b minus, so the second term is m perpendicular by T2 minus mz minus mz equilibrium by T1, and the fourth term is gradient of d grad into m minus m equilibrium. This is the fourth term. So, each of this term in the Bloch equation is the first term represents the precession of the spins around the magnetic field B. The second and third terms represent the rate of relaxation of magnetization. The T1 denotes the spin lattice relaxation time, which determines the rate at which mz returns to its equilibrium value. And we saw that T2 represents the spin relaxation time, which describes the relaxation to state of quasi-thermal equilibrium. And the fourth term basically describes the time evolution of the magnetization M when the sample is also put into a magnetic field gradient. So, very clear here, if you remember these terms, the meaning of these terms in the equation, then you will see that the second and third term are the terms which represent the relaxation rate of magnetization. Question number 12, it's more of a direct question. The reduction in the width of resonance line of spin-spin and spin lattice relaxation rates is known as. So, this also we have seen that diffusion contributes to the spin lattice relaxation rates and spin-spin relaxation rates. So, basically this line width becomes narrower and narrower, and that is known as motional narrowing. So, the narrowing of the line width or the rate resonance line of spin-spin and spin lattice relaxation rates is known as motional narrowing. Now, question number 13. Snowick effect is utilized to measure the interstitial diffusion in a cubic metal M at certain temperature. If the lattice parameter of the metal is 0.287 nanometer and the relaxation time is 1 microsecond, calculate the value of the diffusion coefficient. So, we know that from the Snowick effect, the analysis we get D is equal to 1 by 36 A square by tau R, where A is the lattice parameter and tau R is the relaxation time. So, if you put the value of A, which is 0.287 nanometer, and the time is 1 microsecond. Remember, very important in this questions which appear simple, but we find students making mistakes in assignments or in the exam is the conversion of the units. So, A is in nanometers, so you have to convert by multiplying 10 power minus 9 to convert it into meters, and the relaxation time is given in microseconds, so you have to multiply it by 10 power minus 6. So, if you do that correctly, the diffusivity value is obtained as 2.3 into 10 power minus 15 meters square per second. Now, question number 14. Two students of the NPTEL course Diffusion in Solids are studying diffusion effects of solute B on Gauss-Key relaxation in a metal M. The first student uses a strip of thickness 0.5 millimeter and performs study at 300 degrees centigrade. The second student uses a strip of thickness 1 millimeter and performs study at 400 degrees centigrade. Determine the ratio of the Gauss-Key relaxation times they measure. And what is given is, for the self diffusion of metal M, D naught is equal to 2.3 into 10 power minus 4 meters square per second, and Q is 280 kilojoule per mole. This is written wrong. This is the data for the diffusion of solute B in the metal M. Neglect the variation of thermodynamic factor. So, here for a strip of thickness D, we know that the Gauss-Key relaxation time tau G is given as tau G is equal to D square by pi square phi into dB. That means the relaxation time is proportional to D square, whereas it is inversely proportional to the dB. So, therefore, if you see now to calculate dB, you need to use dB is equal to D naught exponential minus Q by RT. Here the values are given. Again, be careful with the units of Q here. You have to convert it into joules. So, if you use that, then you get dB at 300 as 6.9 into 10 power minus 30 meters square per second, dB at 400 as 4.2 into 10 power minus 26 meters square per second. And the thickness we know 0.5 and 1 mm. So, if you put this in this equation and take the ratio, here I have taken the ratio of first to second. So, in that case you get a ratio as 1.5 into 10 power 3. sorry, it is second to first. Now, the last question of the tutorial is, a thin layer of radioactive isotope of B is deposited over alloy AB and annealed at 700 centigrade for 3 days. The specific activity as a function of depth obtained after mechanical sectioning is tabulated below. Calculate the diffusion coefficient dB. So, what is given as is the depth and the specific activity in becquerel per mg. This is a typical data that you get from the Radiotracer diffusion experiments. So, what you need to do is you need to plot, we know that in the case of Radiotracer diffusion, you have C is equal to C naught exponential minus x square by 4 dt, and therefore, usually we plot log C versus x square, which is a linear plot, and the slope of that gives you the value of diffusion coefficient. So, what you need to do is basically plot log of C versus the x square. This is a micrometer square here. So, the slope of this you can obtain here. So, you can use either Excel or you can use Origin or any other software which allows you to fit this data, and you get the value as this. So, this is the slope. Remember, the slope is negative, and the slope is related to the diffusion coefficient like this. So, this is the equation, and the slope is equal to minus 1 by 4 dt. So, if slope is minus 0.3591 into 10 power 12 meters minus 2, why this is coming, this factor is because the x is in the microns. So, you have to convert the slope according micron square rather. So, the slope has to be converted by multiplying by 10 power 12. So, the dB is equal to minus 1 by 4 into slope into t. T again, you remember here that T is written as 3 days. So, do not forget to convert the days into seconds, and therefore, once you do that, you will get the value 2.68 into 10 power minus 18 meters square per second. So, this way you can determine the diffusivity. Of course, you can say that I do not need to use a graph, but I can also take a couple of data points and just directly determine. You get a more reliable estimate when you plot a graph and see and calculate the value of diffusion coefficient. But even if you want to take 2 points, just check, just try out for your own understanding how much the difference that you get. So, with this we end this tutorial lecture, and next week we will continue with talking more about the diffusion paths and so on. Thank you.